Okay, so for the complexity of the programming, that is basically number of the operations you did for solving the problem. Let's remind ourselves one more time how we do the Gauss elimination, why it has the complexity of the order of n cube. Okay, so the step one for the Gauss elimination basically is convert our current system into an upper triangular. Okay, to the upper triangular matrix. And how we do that in the programming, we will use a loop for converting to the upper triangular. So let's write a for loop for k equals to 1, 2, 3, until n minus 1. That is the column. Okay, so we don't need to do the last column, but we need to do from the 1 until to n minus 1 and trying to make the column lower triangular to be 0. So it's from 1 to n minus 1. And in this loop, for each column, we also need to do each row of the system. So for j equals to k plus 1, k plus 2, until n, basically from the second row until to the last row. We need to make all the row for the um, lower triangular part to be 0. Okay, so this is for the all the row below the k, all the row below j. Okay, all the row below j. Then what we need to do is for the j current row number will be equals to, so that will be equals to j minus k times ajk divided by akk. The akk is definitely the diagonal element. The ajk divided by akk is the scaling factor. So you're scaling the factor for the column part and use the current row number minus that part, so that the lower triangular has to be 0, and this will be the new row number for the j. Okay, so that is for converting. Then you add and you scan the whole column as well, so you add that. Okay, this is for the for loop to converting the argument matrix into an upper triangular matrix. And the work count, which is the operations you will do for this system, work count. So for this part, for your system is around n number, so n row. For the column, you have around n column. And for this equations, think about for each equations, this j is not just to represent a number, is actually represent the whole number you scan for this row. So it's around n. The total will be n to the third. The total loops, or you can say the total operations in these two for loops will be around 1/3 n to the third minus n. So it's not exactly n to the third computational expense. It's around on the order of n to the third. So that is the converting the argument matrix into upper triangular matrix. That is the first step for the Gauss elimination. Then the second step, so let's write this. What we have is from A11, x1 plus A12, x2 plus dot 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 A1n, xn equals to B1, A21 x1 plus A22 x2 plus dot 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 A2n xn equals B2. Then going to an1 x1 plus an2 x2 plus dot 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 ann xn equals to bn. Okay, so this is the argument matrix, and we are trying to scan all the rows, sorry, all the columns from the 1, 2 until the n-1 row. And we also scan all the, so we scan one row, and then we also, at the same time, we need to scan when we scan the one column, the meantime, we need to scan the row and trying to make the scaling factors, which is, for example, the A21 divided by A11, so divide by the um, diagonal element until you find the scaling factors. You will trying to use the scaling factor to make this A21 to be 0, A31 to be 0, A41 to be 0 until AN1. And you also need to scan all the rows so that the lower triangular part will be equals to 0. That is what this work counts for. Then the step 2, after that, your system will become an upper triangular system. Then you need to do the step 2 is backward substitution. So after the step 1, what your matrix will look like? It will be A11x1 plus A12x2 plus A1n xn equals to B1. Then A22x2 plus A23x3 plus A2n xn equals to B2 until you have AN xn equals to Bn. Of course, this A11, A12, A1n, or A22, A2n, ANN, those numbers are not exactly the same as previous one because you need elements, row operators on each row, each column, so that it just become, so those A11, A22, A1n, or those A11, A22, ANN, it just represent that your system become an upper triangular system. The number won't be exactly the same. It probably won't be the same. The coefficient probably won't be the same. So the backward substitution is that you first have xn will be equals to bn divided by ann, right? And after that, you know what is your xn. Then what you need to do, you will go to the previous row that you can get xn minus 1 by knowing you bn minus 1 and xn, so that you can get xn minus 1. So that is the backward substitution. For I equals to n minus 1, it will start with n minus 1, n minus 2, until the first row, which is 1, that you will do xi will be equals to 1 over aii, which is the diagonal element of bi minus the sum of from the column I plus 1 to n column aij xj. So for each row, you will trying to solve that xi. And by solving these equations, and this part is basically sum of all the columns besides that unknown elements column. So you will end this, you finish the back substitution. So the back substitution is much easier as compared to the converting upper triangular. You have basically n row to scan. And for each row, this sum term is around n columns to sum. So the back substitution you have on the order of n squared, the computer complexity. So let's summarize about the Gauss elimination computational complexity. Computational complexity. That is basically the definition of computational complexity is the total number of the operations. You know, additions, multiplications, divide, substitutions, they are all counts for the operations. Then what we count, so the scaling factor, for the importance of the Gauss elimination is you have to know what is the scaling factor, right? So scaling factor Aij divided by Ajj. There is a tricky here. So the scaling factor, which is whatever the element in your matrix divided by the Ajj, where the Ajj is your diagonal matrices. But after you do the row operations, or before even doing the row operations, those Ajj can be zero. So it can be zero. Then if you have the zero at the diagonal matrices, the Aij divided by Ajj won't be exist. So to avoid such error, where the Ajj is equals to zero, we usually do the pivoting, okay? So to avoid Ajj is zero, or besides zero, if Ajj is super small, then the Aij divided by Ajj is so large that it's even hard to solve. So avoid Ajj equals to zero, or Ajj is very small, too small. We will do the pivoting. So what is the pivoting? You will swap the row orders. Okay, you will swap the row orders to let the Ajj is the largest of that system. Okay, so you will swap rows so that the Ajj is the maximum. Okay, so swapping rows is one of the elementary row operations that is still within the Gauss elimination. We will swap rows to ensure that the Ajj absolute number is the maximum compared to, for example, we will ensure A11, A22, A33, A44 until ANN are the maximum along all its rows, okay? So that the scaling factor won't go wrong, won't make any errors, okay? That is one thing is very important for Gauss elimination. We want to emphasize one more time, the pivoting. So the pivoting is usually one of the things MATLAB or programming will have in the Gauss elimination. And then after you get the scaling factors, you will have the Ri minus Aij divided by Ajj, which is the scaling factor times the Aj. And that is for the new row of the I. And Uj will be scanned with all the rows. And this I will be, J will be equals to 1, 2, until n minus 1. I will be equals to J plus 1 until n. Okay. So J is represent for the column. You will scan from the first column, second column until n minus 1's column. Then the row I will be basically with the I will be J plus 1 until nth row. Okay. Then for J, I over J, then basically after we converting, so these row operators will like us to convert the upper triangular into, the argument matrix into upper triangular. Then after that, we will do the back substitution. The back substitution, which is n minus 1, n minus 2 until the first row, you will do this xi term to solve xi using back substitution. And that is the order of n squared. Then the previous, the second one will be the order of n to the third, because that is converting the argument matrix into upper triangular. After that, the final will be the total complexity. You need to add all of them. So the total complexity, the complexity will be the n to the second, which is the back substitution, plus n to the third, which is converting the argument matrix into upper triangular, will be estimatedly equals to n to the third, because the n dimension is so large, n to the second is much smaller as compared to n to the third. Here we haven't count for the pivoting, which we already assume that AJJ is maximum. Okay,